Every developer hits this wall. You pass a variable into a function, the function does something to it, and when you check back in the caller, something is wrong, or nothing changed when you expected it to. The bug feels random, but it is not random at all. It comes down to one question that every language answers in its own way. When you hand data to a function, does the function receive the value itself, or does it receive a link back to the original? That distinction, pass by value versus pass by reference, is the foundation of how memory works in almost every language you will ever use. Get this wrong and you will write bugs that are genuinely hard to find. Get it right and an entire category of defects disappears from your code forever. This video builds the mental model from first principles, walks through memory diagrams, shows you the classic traps, and ends with a decision rule you can apply in any language in under 5 seconds. So what is actually happening? When you write a function call, the runtime has to decide what gets placed into the function's stack frame. With pass by value, it makes a complete independent copy of the data. The function operates on that copy. Whatever it does, the original variable in the calling code is completely untouched. With pass by reference, the runtime instead passes a pointer, an address, a reference. The function and the caller are now looking at the same object in memory. A change inside the function is a change that the caller will see. The two models are not about syntax. They are about what is sitting in memory when the function runs. One gives you isolation, the other gives you shared state. Neither is universally better, but if you do not know which one your language is using for a given type, you are flying blind. Pass by value means a new slot in the function's stack frame is created and filled with a copy of the argument. The copy lives at a different memory address. In Python, integers are immutable, so when you call increment of x where x equals 42, the function receives its own local variable n holding 42 at address 0x2000. The caller's x lives at address 0x1000. When the function does n equals n plus 1, it changes its own local n to 43. The caller's x does not move. It is still 42. When the function returns, its entire stack frame is discarded, local n disappears, and the caller's world is unchanged. This is the safety guarantee of pass by value. The function simply cannot reach back up the call stack and affect the variable you gave it. Pass by reference works differently because what gets copied into the function's stack frame is not the object itself but a pointer to the object. Both the caller and the function now hold a reference to the same object sitting on the heap. In Python, lists are mutable objects. When you call f of mylist, the function receives a local variable lst that holds the same memory address, 0x3000, as the caller's mylist. They both point at the same list object on the heap. This is why mutations propagate. When the function calls lst.append of 4, it reaches through the pointer and modifies the heap object directly. The caller's mylist sees that change because mylist and lst are two names for the same object. This is not a bug in Python. It is the design. The pointer itself is passed by value, but the thing the pointer points at is shared. The most important distinction to burn into your memory is the difference between mutating and rebinding. Mutating means you call a method or use index assignment to change the object the pointer already points at. lst.append changes the list in place. Rebinding means you point the local variable at a completely new object. When the function does lst equals 999 in brackets, it creates a new list on the heap and points its local variable at that new list. But the caller's reference still points at the original object. The caller never sees the new list. This is why you can safely write functions that return new values from their arguments without worrying about mutating the caller's data, as long as you rebind rather than mutate. And this is why defensive programming with mutable arguments matters. If you do not want a function to change your data, do not give it a direct reference to it. The swap function is the classic demonstration of this trap. Every programmer eventually writes a function that takes two variables and tries to swap them. They do the textbook algorithm with a temporary variable, swap a and b inside the function and then check the caller and nothing changed. The function swapped its own local copies of a and b. The caller's originals were untouched. In Python there are two clean solutions. First, return both values and unpack them. X, y equals swap of x, y the function returns a tuple and the caller replaces its own variables. Second, pass a mutable container and swap by index. The function mutates the list directly, which the caller sees. Python also gives you the one-liner, x, y equals y, x. This swaps in a single expression using tuple packing and unpacking and needs no function at all. Understanding why the naive version fails is understanding pass by value and reference at the same time. Different languages take very different positions on this. C and C++ give you explicit control. You can pass by value with a plain argument, by pointer with an asterisk, or by reference with an ampersand. Java passes primitives like int and boolean by value and passes objects by reference, meaning the reference itself is passed by value. You get a copy of the pointer. Python passes everything by object reference. Immutable types like integers, strings, and tuples behave as if passed by value because you cannot mutate them. Mutable types like lists and dicts behave as if passed by reference because you can mutate them in place. Go defaults to pass by value and makes you use the ampersand operator to pass a pointer explicitly. Rust replaces the whole concept with ownership and borrowing. You either move a value into a function which transfers ownership, or you borrow it with an ampersand, which is a reference with compile time safety guarantees. C# has both value types on the stack and reference types on the heap, plus an explicit ref keyword for true reference passing of value types. There are 3 bugs that bite developers every day because of this. First, the mutable default argument. In Python, if you write def add item with lst equals empty brackets as the default, that empty list is created once when the function is defined and reused on every call. 2 separate calls share the same default list object. The fix is to default to none and create a new list inside the function body. Second, aliasing. When you write alias equals original, you have 2 names for the same object. Mutating through alias mutates original. The fix is to copy, original in square brackets or original.copy, or for nested structures, copy.deepcopy. Third, passing configuration dictionaries into services. If the service stores a reference to the dict and you mutate the dict later, the service sees the change without being restarted. Pass a copy to the service or use a frozen data structure. All 3 bugs have the same root cause: shared mutable state through references you did not realize you were sharing. The mental model that ties everything together is a single question: is the type immutable or a primitive? If yes, treat it as pass by value. The function gets a copy. Your original is safe. Integers, floats, booleans, strings, and tuples all fall here. If no, treat it as pass by reference. The function gets a pointer to the same object. Mutations will be visible to the caller. Lists, dicts, sets, and any object instance fall here. When in doubt, copy before passing. Copy.deepcopy gives you a fully independent clone that no function can reach back to. This rule works across Python, Java, Go, and most other languages with minor adjustments for each language's specifics. The immutable equals safe heuristic is not perfect, but it is correct 99% of the time, and it will save you hours of debugging. Pass by value gives you isolation. Pass by reference gives you shared state. The type determines which one you get. Mutables are always safe to pass. Mutables require care. Mutation changes the shared object. Rebinding only moves a local pointer. Use copies when you need safety. And once you have this model in your head, you will read other people's code completely differently. You will spot the aliasing bug before it ships. You will know exactly why the swap function does not work without running it. You will understand why your configuration object changed when you never intended it to. Systems thinking means tracing data through memory, not just through syntax. Thanks for watching.